Welcome. My name is Blair, and I'm coming to you from wonderful Vancouver, British Columbia. And today I wanted to talk about advanced applications of gradient boosted trees in structural engineering. Last summer, I came across this awesome Kaggle competition and data set to predict building safety under earthquake conditions. At the time, I was finishing my master's in civil engineering at the University of Victoria, and I couldn't participate. But I was really curious about this data set because it's very rare to have structural engineering data sets. So I made note of it, and finally in the fall, I have been able to come back and work on the data inside a Jupyter notebook and with Python. This really intersects my research because at the time I was comparing machine learning algorithms for building performance and building optimization. And under all sorts of diverse problems, gradient boosted trees were always highly accurate and very computationally efficient. And so I have continued to want to study these this type of machine learning algorithm more. And so in this notebook, we're going to sort of try to apply some advanced machine learning techniques. So the link to this GitLab can be found in the description to this video. The data set can be found on Kaggle, and basically it sort of is represented with all these sorts of different sort of building geometries, different spans, different heights, different floor to floor heights, different size beams and columns, and all these different building parameters are all meant to then try to predict the maximum lateral drift, which is a very important parameter if you're trying to understand the behavior of a building in seismic activity. But moving to why are tree-based models so good at tabular data? Tabular data is columns and rows. But a decision tree itself is just a really basic structure. And basically each node is just a piecewise function, which sort of just says, is it greater or less than a certain value? And it's just sort of classifying data that way. Sometimes in very high dimensions, but it's a very basic sort of mechanism. And it's just building up a lot of those that's sort of then drawing out the knowledge that's in the data. Sometimes you might be trying to predict or classify, we might try to predict values that are random, and then you'd want to use a random forest. And here you'd have multiple trees and then sort of averaging them at the end. And this shows really good prediction capabilities and reduces overfitting when there's noise, random noise in the value you're trying to predict. We're using gradient boosted trees, which is another ensemble method, which is using sort of sequential trees to correct the previous tree. And this is a really powerful predictive model that generates really high accuracy. One of the ways I like to think about it is it's an office building with all sorts of different departments that have different expertise. And the gradient boosted trees really allows that expertise to sort of one of the ways I like to think about it is by analogy of an office building. You can imagine different departments that have their own expertise, but then they can all sort of come together in a meeting sometime and then really integrate that knowledge so they can deliver a high performance project. Another way to think about it is if you had a whole sort of fleet of boats and they were trying to get to a goal, and if you were sort of releasing them sequentially, the later boats could sort of learn from the heirs of the prior boats and then be able to really efficiently get to their goal. Some of the strengths of decision trees are interoperability. You can really interpret the models quite easily and sort of understand what's happening in them. They're very versatile. They can handle both categorical data and numerical data. They can also interpret nonlinear behavior, which are very sort of complex functions that have exponential in them. They're very robust to both outliers and missing data, and they also do a really good job of sort of automatically handling a lot of the feature selection. It sort of knows which is the most important feature and sort of does that all sort of automatically and naturally as part of a decision tree. So tabular data is representative in columns and rows. And there was a great paper recently about why do tree-based models still outperform deep learning on tabular data. And it really comes down to like three things that gradient boosted trees are doing really, really, really well. Models based on decision trees are better at learning irregular patterns. So when the target function has sorts of steps and nonlinearity, it's very irregular. Gradient boosted trees are excellent at picking up those patterns. Also, like that ability for sort of to be able to do automatic feature selection. Uninformative features can really confuse the neural network, but here gradient boosted trees can really like minimize the effects of uninformative features sort of automatically. Another thing is that non-invariant, and so tabular data is just sort of always sort of looking at it sort of straight on and in a very sort of organized way, columns and rows, whereas deep learning with neural nets, you can see a lot more robustness and the ability to turn things around and upside down and reverse them. This is where deep learning is really kind of excel over decision trees. But now I want to just pause and look at the Jupyter Notebook. Okay, so now we're at the really cool part. We're going to show some code here. There's sort of I'm going to summarize 3 different notebooks. One goes over some of the exploratory data analysis steps that I did. Next, we look at some feature engineering and hyperparameter tuning. And lastly, we look at how we may sort of made the final predictions. First, I wanted to look at the target value. You can see in the original data set, it's quite skewed. And so I applied a log transform to it to be able to make it a bit more normalized distribution, which should be easier for the machine learning model to predict. Next, we look at the different correlation, and basically this is just showing that the correlation of features that the height of the building is correlated to sort of the thickness of the columns and the acceleration and whatnot. Not too much interesting information there. We also want to look at any sort of irregular data patterns or any sort of unbalanced data between the testing data and the training data. For the continuous data, like looks pretty equal overall, pretty balanced. Here we have sort of the integer value features. Again, looks pretty reasonably equal, and also the binary features there. In regards to feature engineering, we wanted to look at which sort of features had the biggest influence on the target value. And so for this, we use the well-known shape values. And so you can see here that the period, the magnitude, the periodic ground acceleration, the number of floors, the distance to the fault had a very high influence on the final values. Here you can look at the feature impact by value range, which sort of gives a different visualization of the same values. So again, it shows that the sort of these top 6 here are very influential to the target value. And so we also wanted to understand like where that cost benefit is, and if model performance started to deteriorate if you added too many features. As you can see here, about 4, 5, or 6, you start to see a little bit of a decline in model performance when you add more features. So in the end, we just used 5 different values. It's pretty amazing with 5 values you could get such high accuracy. For hyperparameter tuning, we used the Opportuna Python package. This is a lot of sort of boilerplate to set up those trials and what sort of parameters you wanted to use. But then after using the optimized function, you get this sort of chart of the top 5 most performant parameters for the 4 different types of gradient boosted tree models that we used. It took 48 minutes in total to sort of test all these different combinations. And so using the top models, I actually use something called a stacked model, or stacked regressor. And basically this allows you to use multiple different types of models, and then it sort of makes an extra column when you are training it that has its accuracy. And so that input values near that, it can sort of look at which model was the most accurate around those models and sort of use that target value. And so it's just a way to squeeze a bit more performance out of your gradient boosted trees. So there was quite a lot of setup there as well. But then finally, you can run sort of this cross-validated training to check out the performance of the models. Everything's sort of working well. And then you sort of get to the function that sort of makes your final predictions from the test data. You want to use all your training data that you have. You sort of instantiate your stacked regressor there, fit your training data, and then just run that test data through it. Make sure that you also sort of reverse that log transform in it, and it comes out with this. These are all very reasonable lateral drifts. It's 10 millimeters, 56 millimeters. So those are all reasonable values. So here we have the final best performing parameters for the different types of gradient boosted trees that we used in this this project. It's really, again, really quite amazing that so few features can return such accurate results. It was quite surprising, and you can see here that the error, 0.2 millimeters around, is very reasonable for the error. And so I just hope that you learned something about gradient boosted trees in this presentation. Thanks so much.